So when we're talking about exponents, the first thing we'll look at is like if we have two numbers like 2 to the third and 2 to the fifth power. When you're multiplying two powers that have the same base, what you're really doing is you're multiplying 2 to the third, so it would be 2 written 3 times, times 2 to the fifth, which is 2 written 5 more times, and you end up getting 2 to the eighth power. So that's what that would look like there. And basically what happens is you have 8 2's written down. 1, 2, 3, 4, 5, 6, 7, 8. So that's how you get to the eighth there. So there's a good phrase that we can use when we're talking specifically about properties of exponents, which is just when in doubt, expand it out, which means just write a fully expanded explanation, okay? All right, so then what we can do, write it out, an exponent as repeated multiplication is called expanding the exponent. All right, so the exponent in this case, 8, all right, is, okay, so 8, that's in the product. That is the sum of the exponents 3 and 5. Let me write those down with the appropriate colors. In the factors. Okay, so we had the 5 and the 3 there. That's where they came from here. And together you add those exponents up and you get 8. That's how you would deal with one property of exponents. All right, so there's the term product and the term factors are used here. Okay, so what do those terms mean? So product in this case is the result of multiplying the base 8 times, and we're using the number 8 because it was 2 to the 8th power. All right. The other term we used was the factors. Okay, factors are the simplest form, or I should say the simplified form of the bases. So, and we'll talk about that a little bit more too, but basically like 2 is a good prime number, so it's a good simple number to use for when we're dealing with the bases here. So like I said, today is going to be a lot of review for us. I haven't started looking at grid assignments yet. I haven't started looking at all the quizzes yet. I haven't gotten through all of them yet. I'm going to get those scores back to you guys, hopefully by the end of the weekend. So next Monday, everything will be updated in Canvas for Module 1, so you know where you stand. And we'll move on to Mod 2. So next we're going to talk about these properties of exponents. You don't need to have these memorized. So there's a few different properties here. Okay, you do not need to memorize these. You actually don't even need to know the names. You just need to know, hey, there's a property of exponents that I need to use from time to time. So the first one, it's called the product of powers property, but the way it works is just like our first example up there. If you have two numbers with the exact same base, but different exponents, you can add the exponents together. Okay. So it doesn't matter what the exponent is, like I could say 5 to the third times let's say 5 to the negative first. And that means I would just rewrite this as 5 to the 3 plus negative 1 power. And 3 plus negative 1 is 2, so it's 5 squared. And I end up getting 25. That's an example for this first problem here. So we're just using the variables a and b, m, and n are going to be representing our values here for when we're talking about the different properties. And then I'll give you a numerical example so you can kind of understand what it looks like. The second one, sometimes we'll see a to the m power and then the whole quantity raised to a different power. And that would result in multiplying two exponents together. So m times n. A good example of this would be if we did 3 squared, but then raise that to the third power. You would say 3 of 2 times 3, which is 3 to the 6th power. Okay. And then 3 to the 6th power is, when it's finally expanded, it's 729. So that's the second property. The third property is the power of a product being two numbers being multiplied together. And then you take a power of both those numbers. This one's almost like a distributive property. It's saying, hey, we can raise both numbers individually to that power. So, for example, if I had 2 times 3 to the m power, or not to the m power, we'll say to the 4th power, then that would be like 2 to the 4th power times 3 to the 4th power. We can raise each one individually to the 4th power. 2 to the 4th is 16, 3 to the 4th is 81, and that becomes 1296. That's the power of a product property. And I'm going to go through these kind of fast, but I'll show you some examples on how we use them as we keep moving through here. But hopefully this is review for us. We've seen these properties of exponents before, I'm hoping, in AGS. I think this is an AGS2 topic. Next we have a negative exponent. So if I have a to the negative m power, that would be the same as if I did 1 over a to the m. And then I have to say a does not equal 0. It's important because if I rewrite it as a positive exponent, a is in the denominator of a fraction now, and I don't want that denominator to equal 0. So negative exponent is the first example here. And that would be like if we took 7 to the negative 2 power. That's the same as 1 over 7 squared. So whenever you have a negative exponent, we don't like negative exponents. We want to get rid of them as soon as possible. You can actually just take a fraction and flip it to the other side of the fraction. So if it's in the numerator, move it to the denominator. If it's in the denominator, move it to the numerator. And that's exactly what we're doing here. 7 to the negative 2 power. We rewrite it as 1 over 7 squared. And then that's not too bad because 7 squared is just 49. So it would just become 1/49. The next one we have is called the 0 exponent. That's basically like if you have a to the 0 power. And anything to the 0 power is always going to equal 1. Doesn't matter what the number is. And that follows the same philosophy that a cannot equal 0. So for example, I can say negative 89 to the 0 power equals 1. Doesn't matter what number it is, anything to the 0 power ever will always equal 1. Okay. And then the last two are going to be very similar to the first two. The difference is the first two dealt with multiplication. The last two are going to deal with division. So if we did a to the m divided by a to the n power. Before, when we did a to the m times a to the n, we added the exponents. This time we would subtract the exponents instead. We'd say m minus n, say when a does not equal 0. Okay, so it'd just be a subtraction of exponents instead of an addition of exponents. So we could say something like 6 to the 4th over 6 squared. That's the same thing as writing 6 to the 4 minus 2. Six to the 4 minus 2 is 6 squared. 6 squared is 36. And then the very last one is if we have two different numbers being divided, but they're raised to the same power, we can raise each one individually to that power. And this assumes that b is not equal to 0. So in this case, we could say, like if we had 4/7 squared, we could write that as 4 squared over 7 squared. And that'll make it a lot easier to deal with, because now I can say, well, I know 4 squared is 16, I know 7 squared is 49, so now I've gone ahead and simplified this. It's again like that distribution property where we can just square each individual number. All right, that's the idea for this first problem here. Okay, so now just a question here. So stop to think, why do the a equals 0 and the b equals 0 statements exist in the last four properties? So it's probably not obvious in the 0 exponent property here, but it should be hopefully obvious in the rest of them. I already kind of touched on it a little bit. But what do you guys think? Why does that exist? Why would that be a concern? It's actually even simpler than that. It's just that we don't want 0 in the denominator of a fraction. So yeah. I mean, having zero as a base is not a good thing either. But yeah, we don't want 0 in the denominator of a fraction. That's it. That's the idea here. Okay. So when we're multiplying powers, one thing we want to be careful of, avoiding errors, we do not want to multiply the bases. And what I mean by that is if we had something like 3 squared and 3 to the 5th, a common mistake that's made for these particular problems is the people will say, oh, 2 plus 5 is 7, but then 3 times 3 is 9. So they'll write it as 9 to the 7th, but that is incorrect. So we don't want to do that. We have to be very careful to remember that the base stays the exact same. So it'd be 3 to the 7th power. When in doubt, expand it out. You write it down as 2 3s, and then write it down as 5 more 3s, and then you'll see how many 3s over there? 7. So it's 3 to the 7th power. All right. Here are a couple examples. Evaluate numerical expressions. And the first thing I have here is I've got -4 times 2 to the 5th, and then squared. Because of this outer set of parentheses, I could technically like distribute this 2 through. So I could write it as like -4 squared times 2 to the 5th squared, something like that. And we have to be really careful here with our negative numbers, because if you're on a calculator, I enter negative 4 squared, I get negative 16. And the problem is this is wrong. The answer is not going to be negative 16. The answer is going to be positive 16. And what happens is when I have negative 4 squared, my calculator reads that as negative 1 times 4 times 4. It reads it as negative 1 times 4 squared. So it'll say negative 1 times 4 is negative 4. Negative 4 times positive 4 is negative 16. What I want to do instead is I want to put parentheses around it. And if I put parentheses around it, now my calculator reads it as negative 4 times negative 4. And a negative times a negative is a positive. So it should be 16. So that's why we don't want to do that. We'd rather do the second one instead. So be very careful when you're using calculators here that you want to make sure you're keeping the negative or getting rid of the negative when appropriate. A good rule of thumb is whenever you have something raised to an even power, it should be a positive number no matter what. Whenever a negative number is raised to an odd power, it's actually going to stay negative. That's a good general rule of thumb to write down if you need to. In this example, negative 4 squared is, like I said, 16. And then I get times 2 to the 10th, 5 times 2. And 16 times 2 to the 10th turns out to be 16,384. Okay. And then the last one here, 11 to the 5th power over 11 to the 8th power. I could start by saying let's do 11 to the 5 minus 8 and then to the negative 1. And that would get me 11 to the negative 3 power to the negative 1st power. So I take care of what's in the parentheses first. And once what's taken care of outside the parentheses, now I can go ahead and distribute this negative 1. And I'm going to get 11 to the negative 3 times negative 1, which becomes 11 to the positive 3. And that'd be as simple as it gets. I mean, I could expand that out to get 1,331, but 11 to the 3rd is kind of the answer for that particular problem. Okay, sorry, I've been talking for a little bit of time here, probably about 15-20 minutes. The last thing I want to discuss real quickly before I give you guys some practice problems to work on is scientific notation. So this is something hopefully you've seen in your science classes by now, in physics or chemistry, definitely chemistry. So this should hopefully not be new for us. But just a reminder that scientific notation is always written in a form where we'd say a number is c times 10 to the n power, where 1 is less than or equal to c is less than 10. And so we're saying that the number c is always a number between 1 and 10. And n is an integer value. So I think if you talked about like number of moles in a chemistry class, it was always like 6.02 times 10 to the 23rd. And that 6.02 is representing a number between 1 and 10. And then the 23rd power is representing an integer. That's the n value. That's how you would always see scientific notation written down. One more example to look at, and then I'm going to give you guys a couple minutes to work on these 4 problems. A swarm of locusts may contain as many as 85 million locusts per square kilometer, and it covers an area of 1,200 square kilometers. So how many locusts are there in the total swarm? So first, 85 million locusts is going to look like that, 85 million. If I wanted to write that in scientific notation, I write as 8.5 times 10 to the something power. I want it to be a number between 1 and 10. The way I'd represent 8.5 is I would start over here and I would move the decimal over how many spaces I need to. 1, 2, 3, 4, 5, 6, 7 gets me a decimal to 8.5. So this would be 8.5 times 10 to the 7th. If I were just looking for the number of locusts in 1 square kilometer and I wanted to write that in scientific notation, it'd be 8.5 times 10 to the 7th. Sometimes your calculator gives answers in scientific notation because your number is so big. So you need to know how to read that on your calculator, what that means. Okay. So for this particular problem though, we would take 85 million and we'd multiply that by 1,200 kilometers. And putting that in our calculator, we're going to get something that looks like 1.2 E11. All right, and that is actually scientific notation. It's got a number between 1 and 10. The only difference is it has this E written down, and the E actually represents 10 to the power. So it's 10 to the power, to the 11th power. That's what this E represents here. And then we still have the 1.2, which is 1.02, which is a number between 1 and 10. That's the reason it's a 1.2. All right, so that covers scientific notation and just a couple examples. Now I want you guys to try the first 4 problems. Try these examples, simplifying as much as possible. You don't need to list the property used, so you can just cross those out. As like I said, I'm not worried about memorizing the properties. I'm not worried about the names of the properties. I just want you to know that these properties exist and I know how to use them. That's what we really need to focus on. So try these 4 problems now. I'm going to give you guys about 5 minutes to work on that. So first problem, 4 squared and then to the 3rd. We could technically start in the parentheses and just, you could start by either saying 4 to the 2 times 3. That's a good way to write it. So, and then that would really become 4 to the 6th power. And then we can finally expand that. 4 to the 6th power is 4,096. The second problem, it's technically a negative 8 to the 1st power. So you could write it as negative 8 to the 1 plus 3, which is negative 8 to the 4th power, which also coincidentally becomes 4,096. Okay, that's the idea for the first 2 problems. Problem 3, 2/9 to the 3rd power. That'd be like 2 to the 3rd power over 9 to the 3rd power. And 2 to the 3rd power is 8. 9 to the 3rd power is 729. And then the last problem, there's a little bit of work to do on this one. Because it starts as 6 times 10 to the negative 4th over 9 times 10 to the 7th. The first thing I see is this 10 to the negative 4th. I want to get that to the bottom of the fraction. So I'm going to write it as 6/9 times 10 to the 7th times 10 to the positive 4th. That's how you get rid of a negative exponent. And then 6/9 could technically simplify a little bit. That could become 2/3. You get 2 over 3 times 10 to the 7 plus 4. So it becomes 2/3 times 10 to the 11th. All right. And that's really like the simplest we're going to get there. The last thing you could do is put it in your calculator and you'll get an answer in scientific notation. It should say 6.67 times 10 to the negative 12 when you put it in your calculator. And again, you'll probably have the E button or the E written there. So you just need to know what the E means. You're going to rewrite that in scientific notation. All right, so that's those 4 examples there. Okay. Let's see. Last thing I want to talk about today is simplifying expressions. So you can use the properties of exponents to simplify algebraic expressions. That's really important. And a simplified expression, when we're simplifying them, should contain only positive exponents. So we don't want any negative exponents in our simplified expression. That's really important. No negative exponents, positive only. So that's usually one of the first things I want to do when I'm simplifying expressions is try and rewrite it so there's no negative exponents at all. And that's what I did on number 4. How the first thing I did was to say, let's get rid of this negative 4 exponent and move it to the denominator. And then we can work through everything else after that. Okay. Just another thing I wanted to talk about was these first 3 problems. It's saying that expanding it out would actually work just as well. So for example, we know that this came out to 4 to the 6th. So if you write it out like this, you'd say 4 squared to the 3rd power. 4 squared to the 3rd power would just be writing 4 squared 3 times. And then you would write each 4 squared twice. And what happens is you end up with 1, 2, 3, 4, 5, 6 4s. So that's 4 to the 6th. With the second problem, negative 8, you'd write out negative 8 3 more times. And you'd end up with 1, 2, 3, 4 negative 8s. And that's what we saw. That's what we saw above as well. And the last one, if we wrote out 2 ninths 3 times, you get 2 ninths times 2 ninths times 2 ninths. That would end up being 2 times 2 times 2 over 9 times 9 times 9, which is 2 to the 3rd over 9 to the 3rd. So properties of exponents allow us to save these steps so we don't have to write out the expanded out part if we know how to use the properties appropriately. That's the key for the properties of exponents. Okay. Order of operations. The last thing I want to talk about today is just making sure we can follow order of operations as best as possible, and that'll help keep things simple. So for example, on the first one, b to the negative 4th times b to the 6th times b to the 7th, we would just follow order of operations from left to right there. So you could technically write this as b to the negative 4th plus 6. And that'd be the first thing you could do. You get negative 2. And then you could write b to the negative 2 plus 7. And you get b to the 5th. All right. That's how example A would be written.
Wait, negative 4 plus 6? Wouldn't that equal 2?
That would equal positive 2. Thank you. Yes. Way better. So we're going to do positive 2. And then you have b to the 2 plus 7. That would equal b to the 9th. Thank you. Yeah, so you got it. You got the right idea. Okay. So that's one way to do this type of problem. There are a few different ways you could do it. Like, because it's a negative exponent, and I said we don't want to deal with negative exponents, we could technically write this a different way and say, let's move that to the denominator and write b to the 6th, b to the 7th over b to the 4th. And if you're in doubt, you could expand it out. You could write 13 b's on top. One, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13. 4 b's on the bottom. And then say, okay, I gotta divide out some b's. 1, 2, 3, 4. And then how many b's am I left with? 1, 2, 3, 4, 5, 6, 7, 8, 9. And I get b to the 9th that way. So that's when in doubt, expand it out. But that can get really nasty if you have to write down like 24 of one variable or something like that. So it's best to try and learn the properties to try and avoid those situations. Example B, I have an r to the negative 2 in the parentheses. So I'm going to write this as r squared, s to the 3rd. and then that whole thing's to the negative third power. And the negative third power means I can flip the entire fraction inside and rewrite it to the positive third power. So first thing I did was I dealt with what's inside the parentheses. I got rid of that negative first. And then the second thing I did is I got rid of the negative outside the parentheses. And now the last step is I'm going to write this as r to the 2 times 3, s to the 2 times 3. Distribute that 3 and make sure that's multiplied by both variables here. And that gives me r to the 6th, s to the, oops, so it should have been s to the 3 times 3, sorry, s to the 9th. And then there's a 1 in the denominator that we don't really need to worry about anymore. So r to the 6th, s to the 9th, for example, b there. So this is how we'd want to simplify these. It's going to be a lot easier to deal with r to the 6th, s to the 9th than it is to deal with this whole big thing that we started with. So that's why simplification is important. Example C, we have 16 m to the 4th, n to the negative 5th, and 2 n to the negative 5th. The first thing I see here is 16 divided by 2. What's 16 divided by 2?
8.
8. So I have 8m to the 4th, n to the negative 5th, over n to the negative 5th. Next thing I've got is I got these n to the negative 5ths that need to switch where they are. So I have 8m to the 4th, n to the positive 5th, over n to the positive 5th. And then technically, because there's an n to the 5th on the top and an n to the 5th on the bottom, I could write n to the 5 minus 5, which is n to the 0, and n to the 0 is just 1, so I end up with 8m to the 4th. Something else you might recognize or notice is like, hey, I have n to the 5th divided by n to the 5th. That's 5 n's on top, 5 n's on bottom. I could just cross those out earlier on, and that could save me a lot of work. All right, so starting to recognize those types of patterns when I have the exact same thing on top as I do on bottom. That's just like 7 divided by 7 is going to be 1. Okay, so it can simplify out a little easier that way. Okay, the last one here, part D, I have x to the negative 3rd, y to the 3rd, and then squared. I'll start by distributing that 2 through. We'll get x to the negative 3rd times 2, y to the positive 3rd times 2. Because the bottom part wasn't being raised by any extra exponents, so I'm just going to keep the bottom part the same. And I get negative 3 times 2 is negative 6. 3 times 2 is positive 6. All over x to the 5th, y to the 6th. One thing I noticed right off the bat, I have a y to the 6th divided by y to the 6th. So I can get rid of those. Excuse me. Something else I noticed, I have an x to the negative 6th that I need to move to the denominator of the fraction. So I get 1 over x to the positive 6 times x to the 5th, which is 1 over x to the 6 plus 5, which is 1 over x to the 11th. And that would be as simplified as this is going to get. But 1 over x to the 11th is going to be a lot easier to deal with again than what we started with way up here with this whole nasty thing. We got rid of a variable, even we got rid of all the y's, which is kind of nice. Okay, so that takes care of those examples. Now I've got 4 practice problems I want you guys to try, and that'll be the last 4 things we do today. So try these practice problems. I'll put the answers up in just a minute here. And then it looks like we're going to get out of here a little bit early today. Okay. So in these last 4 answers, just make sure you followed through them correctly. There's a few different ways you could work through them. So the method I use doesn't necessarily have to be the method you use. Just as long as you're following the general order of operations, the general principles, you should be able to get the same answers as I did. Just so you know, there's not going to be assignment number 10 tonight. I was going to give this before the graded assignment, so I decided not to do an assignment, so you could just focus on your graded assignment, but then I decided to push it back a day, So there won't be an assignment tonight. We'll start on Mod 2 tomorrow. We'll have an assignment due. But the whole idea here is that you guys can just relax a little bit, get ready for more Mod 2 stuff tomorrow. We need to have these properties of exponents, good foundation on them to be successful in this next exponential unit, the unit that's on exponential functions. All right, so that covers everything for today. Have a great